So now, having seen the problems involving mathematical induction, we are now ready to start permutations and combinations. Now, in this type of problems, what we are concerned about is arrangements of objects. We are given some objects and we are concerned about arrangements of those objects, and really we are not really concerned about the arrangements themselves, but rather how many arrangements are possible. For example, if you consider this word cat, it has three letters, right? Now these three letters are distinct. One may ask, in how many ways can we arrange these letters? You can see that I can arrange them in these different ways. C, T, A. Then I can have A in the beginning, then I can write A, T, C, A, C, T. Like that I can write T, A, C, T, C, A. These are the possible arrangements of these letters, of the letters in the word cat. Now how many of them are there? 6. 1, 2, 3, 4, 5, 6. So there are 6 arrangements possible of the letters of the word cat. Now we are concerned about this number 6, and we want to be able to determine this number without finding out all the arrangements, without actually writing down all the arrangements. That's our aim. Now, before we try to figure out how to get this number 6 without writing these things, let us see a bigger question. A bigger question means the same question but with a bigger example. Say I have the word rose. Now here, say I want to do the same thing. I want to find all the arrangements of the letters of this word. Now in this case, as you can already imagine, there will be many more, simply because there are 4 letters. So let us try to systematically write all of them first of all, since at this stage we don't really know how to get this number 6, or for example, in case of rose, what will the number be? That also we don't know at this stage. So let us first of all write all the arrangements. The first one of course is rose, and then we keep, okay, see, just like how we found the arrangements in this case, here also we try to do similar thing. So what we do, you see, at first we kept C fixed, then interchanged A and T. Interchanging A and T actually means finding all the possible arrangements of these 2 letters, A and T. And there are only 2, either AT or TA. So the same thing we are going to do here, only with 3 letters, O, S and E. So I can keep O fixed and interchange E and S. Then I can start with S. I can write like this, R, S, E, O. And then finally I can start with, I started with O with S, then I start with E. S, O, R, E, O, S. Okay. Now in these arrangements, R is appearing in the first position. That I can do with all the other letters. So say I can start with O. Then I will be left with R, S and E. Then I change the positions of these 3 letters, keeping O fixed. R, E, S, O, E, R, S, O, E, S, R, O, S, E, R, O S R E. Then I do the same for say S, R O E, S R E O, S E R O, E O R, S O R E, S O E R. And finally I can do that with E in the first place, E R O S, E R S O, E S O R, E S R O, E. I had R and S, so now I write O R S, E O S R. So these are all the possibilities, all the possible arrangements of the letters of the word rose. Now, how many of them are there? You see, I have 4 columns, right? In each column I have 6 entries. So the total number of arrangements here is 4 times 6 is equal to 24, right? Now, instead of going to even a more complicated situation having say 5 objects, now although I have taken here words and their letters, that's not necessary. You are not always supposed to take words. You can take any objects. You can say take a pencil, a pen, a piece of paper, and say a pencil sharpener, something like that, any objects. The only thing we are maintaining here is that at this moment we are taking the objects to be distinct. Okay, now a situation will come later on where the objects can be repeated, so we will see that later. So first of all, we are dealing with the situation where the objects are distinct, right? Now, instead of looking at a more complicated example, we can in fact look at a very simple example. Suppose we look at the word at. Now, in how many ways can these letters be arranged? Of course, 2 ways. Now, do you see a pattern here? You see, 6 can be written as 3 times 2, where this 2 appears here. And what is 3? 3 is the number of distinct objects for which we are trying to find the number of arrangements. If you go to the next case, we have 24, which is 4 times 6. 6 is the previous number that is coming here, and 4 is the number of distinct objects available to us for which we are trying to find the number of possible arrangements. So this pattern suggests that if we have any number of objects, then we can in fact try to find this number of possible arrangements of those objects. And that's what we are going to do. But that actually, if we approach these numbers in this way, that although gives us the number in the general case where we may have any number of objects, then we can write down the number of their possible arrangements. But that will not give us any insight into what is actually going on. Here I have found a pattern and I believe that this pattern is true, and then I will take any finite number of objects and try to write a formula for the number of arrangements of those objects, and then I can prove that formula using mathematical induction. So let us do that first. Okay, let us do that first, and then we will look at the thing from a slightly different point of view, which will give us more insight and will tell you exactly what is going on in these calculations and why are we getting the numbers that we are getting. So here I make a claim. Let n be a positive integer. Let n be a positive integer. The number of ways of arranging n distinct objects the number of ways of arranging n distinct objects along a line is a number that looks like this: n times n minus 1 times n minus 2. This way we are decreasing the factors in size 1 by 1 and eventually we reach 3 times 2 times 1. Okay, this is my claim that if I have n objects, then those n objects can be arranged along a line in this many ways. You see, when n is equal to 3, what is this number? This number is nothing but 3 times 2 times 1, which is 6, and that's what we got there. When n is equal to 4, this number is 4 times 3 times 2 times 1, which is 24. This is also what we got there, okay, by actually finding all the arrangements. Now we want to prove this result using mathematical induction. This is one of the reasons why I solved those problems involving mathematical induction in the first place. Okay, so now the proof is not very difficult, it's actually rather easy. Although this result is of marginal interest, it's actually not a very difficult result or not a very important result that tells you something profound. No, it really tells you something elementary, but nevertheless we want to see how we can use induction in several different places where we can use, okay, and how to use it effectively, because the reason for this is that what I feel is that induction is a method which, if you can use it effectively, then you can produce many proofs in situations where other methods either are truly difficult or okay, we will come to that. Why induction is sometimes the way to move forward, and why induction is sometimes makes the situation quite easy. We will come to that later. Okay, let us first of all prove this one. So we already know what we have to do in induction. We should prove a basis, and then we will consider an induction hypothesis. Based on that, we perform the induction step. Once that is over, the proof is over. Okay, so when we have only one object, the number of ways it can be arranged is of course 1. if you have only one object, say a letter A, then this is the only possible way of arranging it along a line. In fact, it's just like a point. Since you don't have anything else, this is the only arrangement. Is of course 1. And the number means this number. The number is also 1 when n is equal to 1. See, in this type of products, you may think that since we have n minus 1, n has to be larger than 1. Just by looking at this product, we feel that n should be somewhat quite larger than, in fact, 3 also. But that's not the case. In this type of product, you should understand that the product starts from here. You can of course write it in the other way, 1, 2, 3, etc., going up to n, but it starts from 1 and it reaches n. Okay. In between 1 and n, the positive integers that you have, all of them have to be taken and their product is considered. Now, since here n itself is 1, so in this product there is only one factor, which is 1. So that's why this product is 1 when n is equal to 1. So in this case, when there is only one object, the number of ways of arranging that object is 1, which is common sense. But from the formula also we are getting 1. So the formula is true when n is equal to 1. This is the basis for our induction. So now we assume the induction hypothesis. Now assume any n distinct objects can be arranged along a line in this many ways. To 1 ways. Okay. Where let me continue from here. Where n is some positive integer. Okay. Let there are, let me write it in a slightly different way. Now consider n plus 1 distinct objects. Okay. Now consider n plus 1 distinct objects. Now if you go back to that cat example, right, or for example the rose example. So there what we were doing, we had 4 places, right, and those 4 places are to be assigned some letters. Each one of them will be assigned a letter of this word. Now, you saw that when I wrote R in the first place, then the remaining 3 letters or the remaining 3 places can be assigned these remaining 3 letters in how many ways? 6 ways. Okay, excuse me. So the remaining 3 letters can be assigned in 6 ways, because you can arrange O, S and E in 6 ways. Now this is happening only for R. For O also we had 6 ways of arranging the remaining letters R, S and E. For S also we had 6 ways, and for E also we had 6 ways. That's what gave us 6 plus 6 plus 6 plus 6 equal to 24. So, or 4 times 6 is equal to 24. Okay? So, what I am trying to say here is that out of these n plus 1 distinct objects, if I choose one object first, then I am left with n distinct objects. Those n distinct objects can be arranged in this many ways. Why? Because that is my assumption, induction hypothesis. I have assumed that whenever there are any n distinct objects, they can be arranged along a line in this many ways. For one choice of that first object, like this R, okay, here we have how many objects? 4. So you can think of this 4 as 3 plus 1, n plus 1. Now once I have chosen one object R, then the remaining 3 objects can be arranged in 6 ways. For each of my choice of the first object, the remaining objects can be arranged in 6 ways. So that is giving me 4 times 6 equal to 24 ways. Once an object has been chosen from this list of n plus 1 distinct objects, the remaining n objects can be arranged. So since we have understood this part, let me wrap this up. The remaining n objects can be arranged along a line in how many ways? N times n minus 1 times n minus 2, etc. This many ways. Now, these are the arrangements for that first choice of that object, but the first choice itself can be made in how many ways? N plus 1 ways, because there were n plus 1 objects. For example, in rows, I had 4 objects, which is 3 plus 1. So, to choose the first object, I have 4 choices, R, O, S and E. Okay, here I have n plus 1 choices for the first object. Once that choice has been made, the remaining n objects can be arranged in this many ways. So for each of the first such choice, I have this many possible arrangements. So for n plus 1 of them, how many arrangements shall I have? You just add this number how many times? N plus 1 times. 6 plus 6 plus 6 plus 6, 4 times. Just like that, this plus this plus this plus this, n plus 1 times. So hence the total number of ways of arranging, and you can understand what I am supposed to write here, arranging n plus 1 distinct objects along a line is n plus 1 times n minus 1 times n minus 2 and etc. to this. That means n plus 1 times this number. Just like we had 4 times 6. 6 is this number. when n is equal to 3, that is 3 times 2 times 1. Okay, so here n is 3 and n plus 1 is 4. So now what does this tell me? It tells us that we have completed the induction, because if we have n plus 1 distinct objects, by logic we have found that the number of arrangements of them along a line is this. At the same time, from this formula, if we had n plus 1 in place of n, this number would be this. Simply you just replace n by n plus 1, n plus 1, n minus 1 and so on. Okay. So we see that using mathematical induction, this claim has been proved, and then you write this completes the induction and hence our claim is proved. Now, so we know that this many ways we can arrange a list of n distinct objects. Now we can apply this result to some situations, some rather simple situations. Say for example, if I had 5 objects, okay, 5 distinct objects, instead of now going to a word, these 5 objects can be arranged in how many ways? Now you have the formula, you just write this number, 5 times 4 times 3 times 2 times 1. Although we need not write 1 since it does not affect multiplication, but still we are writing for the sake of symmetry. So we already know what is this number. This is 24. So this gives us 120. So you see that as the number of distinct objects is increasing, this number of possible ways of arranging them is actually increasing at a very high rate. We had 6, then we jumped to 24, then 120. Then after that the numbers keep increasing at a very high rate. Anyway, now the thing is that although we have found this formula, but we really don't know why the formula looks like this. See, this is why mathematical induction makes life easy. Simply because it bypasses the understanding. Sometimes if something is really complicated and you are able to prove the thing by using mathematical induction, what it does is that it doesn't tell you actually what is going on inside the proof. A direct proof will tell you exactly why the result works, but a mathematical induction will bypass that complexity. So sometimes that's why it's the only way forward if things are really that complicated. But in this situation, we need not have actually found this using mathematical induction or proved this using mathematical induction, because although we now have all the answers in this case, we still don't know why 6, why 24, why 120, why are these numbers being multiplied. So now we have to understand that. So let us go back to that cat example. Okay. So let me quickly write all the possibilities. A, C, T. Now if we look at this number of possible, this possible arrangements, what we are doing is that we have 3 places along a line. Now why I am saying along a line all the time, it's because if I have them along a curve that is closed, say for example like something like this, I have these places which Say some people are sitting around a round table. Okay. Now how many ways they can sit so that we have different arrangements. Now in this particular case where things go one way and come back, okay, that creates a slightly more complicated situation. So we will come to this later on. It is called circular permutation. Now we will come to that later. But if we have an arrangement where the objects are arranged in along whatever curve, not just see, that's why I am not saying straight line. The objects can be arranged along a curve like this, or maybe it can be arranged in some grid fashion. Okay, whatever be the case, this is the case we are considering now. That circular case, it creates extra complexity. We will see that later. Now, for the case at hand, we want to understand why the number 6 is appearing not using this formula. In fact, we want to know why this formula is like this. Okay. Now, see, that is the way we have to think in this type of problems. It's not all, you see, if you think that for every case you will have a formula which you will memorize and then you will recall from your memory and use it effectively to get the answer, that is not mathematics. That is just, for example, you have written a program, a computer program, you give some input to that computer and it searches for the appropriate formula and gives you the answer. Computer cannot think, but we can think. So our approach should not be that mechanized. And that is the mistake people do while studying mathematics. We have to really understand why something is the way it is. So why this number 6 is appearing, that's what we are going to try to figure out here. You see, we can put letters here, either C or A or T in each of these things. Now, if I write C here, I am left with two possibilities for these remaining two places, A and T. If I write A here, I am bound to write T here. But if I write T here, I have to write A here. So this single C is producing two different arrangements, CAT and CTA. Similarly, A is producing two different arrangements, ATC and ACT, and T is producing two different arrangements, TAC and TCA. Okay. So let us look at this in this way. For the first box, I have three possibilities, either C or A or T. Once I have chosen the first box, then I am left with two possibilities. Those two possibilities in each case is different, right? So, for example, when I have C here, I have A and T. When I have A here, I have T and C. When I have T here, I have A and C. But the different types of letters don't matter. What matters is that once we have chosen something here, we are left with two possibilities. This number 2 matters. So, for the second box, I can write either A or T. Okay. So for the first box, I have three possibilities. For the second box I have 2, and for the third box of course I have only one possibility. Now you have to keep in mind, in what sense are we saying 3, 2 and 1? 3 here in the beginning